Today we'll cover airspeed calibration data reduction for the Piper Cherokee 6. These are the flight cards you'll fly with. On the front card, you'll have general information at the top, which includes the aircraft tail number, date, fuel load, gross weight, and CG, and various times. The test crew information will be in the middle, and the overall planned flow of test points will be shown. On your data card, you'll write down which test point was flown and the various data that's needed. This is the primary data. Airspeed and altitude will be taken either from the second or third row. Indicated heading, GPS, ground speed, track, and outside air temperature will be taken from the co-pilot seat. This is the secondary data. RPM, manifold pressure, fuel quantity, and time of day. This data is not needed for data reduction. Flaps is the configuration, which would be either up or down, and for all this data taken, flaps remain in the up position. The left front cockpit has the pilot's airspeed indicator in miles per hour, altitude in feet, heading in degrees magnetic. Note that the airspeed indicator and the altimeter that the pilot uses is connected to the production pitot vane. The total pressure inlet is the hole in the front of the vane. The static pressure inlet is the tiny hole in the back of the vane. In the center front cockpit, you'll see fuel quantity or fuel burned will be read out in a digit form on this gauge. GPS ground track in degrees magnetic and GPS ground speed in knots are read from the Garmin 430 in these windows. On the right side of the front cockpit is engine manifold pressure in inches of mercury and engine RPM. Outside air temperature comes from the temperature probe located above the pilot's head through the windscreen above the visor. On the opposite end of this temperature probe is the temperature gauge. The inside numbers are degrees Celsius. The outside numbers are degrees Fahrenheit. We'll be using degrees Celsius. In the second and third row, you'll find airspeed in miles per hour and altitude in feet. You'll want to set the Colesman window on your altimeter to 29.92 to get pressure altitude. These gauges in the second and third row are connected to a separate pitot-static source than the pilot's instruments. Total pressure comes from the test probe pitot, and static pressure comes from the alternate static pressure inlet on the side of the airplane. To review, here's all the data you'll need for this flight. Again, airspeed and altitude comes from either the third or second row. Indicating heading comes from the pilot's gauge. GPS ground speed and GPS track come from the Garmin 430. Outside air temperature comes from the temperature probe. RPM and manifold pressure come from the co-pilot's gauges. Engine quantity comes from the fuel quantity gauge. Time of day comes from your watch. And flaps is either noted as up or down for this flight. Determining the airspeed indicator correction, or delta VIC, from an engine chart. Each instrument comes from a lab, and the lab produces a scale air chart. In this case, the technician will set an indicated airspeed using a manometer, and that's the truth. The technician starts at 20 miles per hour and then reads the instrument. The instrument in this case read 22 miles per hour, so there was a plus 2 mile per hour scale error. The tech then increases the airspeed to 30 miles per hour, the truth airspeed that is, and then reads what the indicator says. In this case, 31 miles per hour, or plus 1. The tech continues this until 150 miles per hour. At that point, the tech then goes in the reverse direction, stopping at 140, 120, 100, etc. All the same points that the tech used on the way up. that tech will stop on the way down, and this establishes if there's any hysteresis in the gauge. Clockwise, or CW, means readings were taken while airspeed was increasing. Counterclockwise means readings were taken while airspeed was decreasing. For propeller aircraft like the Cherokee 6, there's always vibration in the cockpit, so we can neglect hysteresis and simply average the two scale errors. The instrument corrections, delta VICs, are the opposite or negative of scale error. I created here another table. I grabbed indicated airspeed that was our truth airspeed. Then I averaged the two scale errors for this column. I then set the instrument correction, delta VIC, to negative of the scale error in this column. And then this is what our airspeed indicator actually read during the test. From this tabular data, I can then create a plot of delta VIC versus indicated airspeed to interpolate for other airspeeds not listed in the table. To get instrument corrected airspeed, I'll take whatever indicated airspeed I have off my gauge, and then I'll grab a delta VIC from this chart and add that to the indicated airspeed to get my instrument corrected airspeed. Similarly, we can do this for the altimeter. Again, each gauge comes from the manufacturer with a scale error chart. In this case, hysteresis was not looked at. The tech just simply increased altitude the whole time and took the readings. So we'll take what we got. Here's the truth altitude, the scale error. Again, instrument correction is the negative of the scale error in this column, and this is what the actual instrument read. Once we have this tabular data, we'll again create a chart, a plot of delta HIC versus indicated altitude, and that way we can get our data for altitudes not in the table using interpolation. Same thing, to get instrument corrected altitude, we simply read off our indicated altitude in our flight, find the associated delta HIC, add it to the indicated altitude, and that gives us our instrument corrected altitude. Data reduction. Step one is we take our indicated readings off our flight card and apply the instrument corrections we just found using those two plots to calculate our instrument corrected airspeed and instrument corrected altitude. In this case, for test point 1, I grab 107, I go to the chart or the plot, that's the delta VIC, and so that's my instrument corrected airspeed for test point 1. Likewise, I grab altitude, that's my indicated altitude, plus the correction gives me my instrument corrected altitude. Test point 2, 108, off the chart, gives me my instrument corrected velocity for test point 2. For altitude, I grab this altitude, grab the correction off of the chart, and that's my instrument corrected altitude. For step 2, I calculate the angular difference between the airplane magnetic heading and the GPS magnetic track. So the data comes from indicated heading and GPS track. For test point 1, they were aligned, so there was no difference in angle. For test point 2, we had a 2-degree difference in angle. This was not a very windy day, so these were fairly close. On windier days, this angular difference could be more substantial. Step 3, calculate corrected ground speed. Here's the equation for corrected ground speed is our ground speed off our GPS times the cosine of the angular difference we just calculated in step 2. For test point 1, ground speed 82.4, cosine of the angular difference is 82.4. Again, ground speed, cosine of the angular difference gives us 108.93 in this case. Step 4, calculate atmospheric pressure ratio. Here's the formula. Delta is atmospheric pressure ratio. Simply take our instrument corrected altitude that we got in step 1, substitute in here and calculate delta. For test point 1, delta sub 1 is the instrument corrected 2427 altitude that we got in test point 1. For delta 2, we we put in our instrument corrected altitude of 2547.6. Step 5, calculate atmospheric temperature ratio. Here's the formula, 273.15 plus outside air temperature that we got off the gauge divided by 288.15. For test point 1 and 2, the outside air temperature was the same at 22 degrees Celsius, so these numbers are the same. Step 6, calculate the square root of the atmospheric density ratio. Density ratio is the ratio of pressure ratio, delta, to temperature ratio, theta, and the square root is just the square root of that. So we grab our delta from test point 1 and our theta from test point 1, ratio those and take the square root, gives us 0.94533. Likewise for test point 2, we grab delta from test point 2, theta from test point 2, take the ratio and the square root, gives us 0.94323. Step 7, calculate calibrated airspeed. Calibrated airspeed is our corrected ground speed times this square root of the density ratio. Our calibrated ground speed for test point 1 is 82.4. So we multiply that by the square root of that density ratio, gives us 77.89 knots. And for test point 2, we get 102.75 knots. Step 8, calculate average calibrated airspeed and average instrument corrected airspeed. The way we do this is we take calibrated from one heading plus the calibrated from the opposite heading, divide by 2. For our instrument corrected airspeeds, we take the instrument corrected airspeed from one heading, add the instrument corrected airspeed for the opposite heading, and divide by 2. Test points 1 and test point 2 were flown at opposite headings, so we can calculate our average calibrated airspeed and our average instrument corrected airspeed. At this point, note that these are in different units, so we'll have to take care of that. For step 9, we're going to calculate the position correction, which is the difference where we take calibrated airspeed and we subtract off our average instrument corrected airspeed. But again, we got to get in the correct units. We're going to put it in miles per hour, so we'll take our calibrated airspeed, which was in knots earlier, multiply it by 1.15 and get our calibrated airspeed in miles per hour. Now I can subtract our average instrument corrected airspeed for test points 1 and 2 and arrive at our delta phi PC, or our position correction, of negative 2.82 miles per hour. As you can see, this type of data analysis lends itself to a spreadsheet where you put in indicated airspeed and altitude, you put in the delta VIC and delta HIC off the graphs, calculate instrument corrected velocity and altitude, track and heading come from the data card, we calculate the difference, we get GPS ground speed off the data card, we correct that, delta, OAT, theta, square root of sigma, get our calibrated airspeed, our average calibrated airspeed, convert that to miles per hour. Here's our average indicated airspeed in miles per hour. This is our average of instrument corrected airspeed in miles per hour. This is our average indicated airspeed in miles per hour, and this was the corresponding delta V PC. So we'll plot this data down here, and we'll smooth or fare a smooth curve through the data because it is aerodynamic data. So we want that to be smooth. And notice in this case, I did have an outlier that I did not want to put in the curve fit, so I still plotted on the plot, but I chose to ignore it. Likewise, you'll generate a plot of delta VPC versus indicated airspeed for the flaps down data. There's the data that I recorded from flaps down configuration. Again, it lends itself to a spreadsheet in the same manner as you used for flaps up, and you'll get a different delta VPC versus VI curve for flaps down.